Check 2, 3, 4. People hear me? Wow, does that take me back? In 1969, I was a roadie for a very early psychedelic rock band called the Travel Agency. And how the booking agent succeeded, I don't know, but we wound up with a 12-stop tour through Texas and Oklahoma in 1968. They had no clue what we were. So doing sound checks takes me right back. Fortunately, that is a very, very ancient history, and today is technology. This talk is a highlights talk of the first 3 full-length talks, which together are almost 5 hours, and we're not going to ask you to sit through 5 hours, but you can find them on the website. In several cases, I'll wind up saying there's more. You have to see the videos that are there. I will be here for the rest of the afternoon. If there's questions or you want to go in greater depth or some of the things that I'm skipping over doing the highlights, I'm here and I'm happy to answer everything I can that the U.S. Patent Office will permit me. We're a commercial company, so we're driven by the market. What the market wants is high throughput, low power, low cost. Easy enough. How to achieve high throughput, low power, and low cost has been known for 40 years. What you want is a very wide issue. This gives you your throughput. You want to have static scheduling. This gives you your low power, especially if it's an exposed pipeline, gives you low power. And you can buy such chips today. The mill, the out-of-the-box computing architecture, is one such chip. To qualify terms, which for this audience may be unnecessary, the mill is a wide-issue machine like a VLIW or the Itanium. That is, individual instructions hold multiple operations. Lexically ordered within the instruction, the individual positions for the operations are called slots. So if you hear me talk about an instruction slot, that's what that is. And they correspond to individual functional unit pipelines, which when the decodes one of these instructions, it routes the operations to the matching pipeline where the individual functional units in that pipeline execute them. It's an exposed pipeline machine. Every operation has got a fixed latency. To take an example, the sum and product in this little expression are independent of each other and can be executed in parallel because we're a wide issue machine. You can have an instruction with both an add and a multiply in it. These will be routed to an adder and a multiplier in 2 different slots and 2 different pipelines. The dotted pink line there means a cycle boundary. Sometime after that, we will have the results of the add and the multiply, and we'll now want to have an instruction containing a subtract. There may be other operations within that instruction. And that will, of course, require a subtraction unit, which again will be just an ALU, but we'll call it a subtraction unit. After that first cycle, the adder is done, so we've got an A plus B result coming out of that adder, but multipliers are not one-cycle operations. So after that first cycle, we don't really have a multiply result. It's in flight inside the multiplier. So another cycle, and now what we have is the product available, and the result of the add is now available one cycle later, which can, of course, now feed into the subtract. A cycle after the subtract, we have our final result. Now, when we do this is the question of who holds and how are held the intermediate results, which are not going directly through a bypass from one functional unit to another functional unit. It's best if your code doesn't have anything being held. Instead, you schedule your operations so that the results come out just before the consumer wants them and can consume them directly, and you don't have to keep them around. The The mill is a family architecture, like the 360 was a family, and the x86 has evolved into being a family. They share a common architectural basis. A load module that runs on one mill will run on any other mill, but they vary widely in power and performance based on individual market niches. Gold here is an example. It's a middle to high-end chip. Each instruction can issue up to 33 individual operations per cycle as one instruction. The clock rate is 1200 megahertz in our initial anticipated physical hardware. Incidentally, we've been running in SIM for several years, but I can't give you something in a plastic pack and won't be able to give you something in a plastic pack for a couple of years now. So what we're describing here is an architecture and simulated rather than something that you can buy.
Okay, ask why it'll be a few years?
Again, please, I'm slightly deaf.
Why a few years?
Because it takes that long.
You started it?
We have indeed. Portions that are very long are done, some of the critical pieces. But a chip from scratch is a lot of work, especially a rich architecture like this. We anticipate in this actually, I believe, was for a 30 nano where this number comes from, but I no longer recall. I'm a software guy, not a hardware guy, and I'm quite likely to grossly mislead you with these things. 14 watts, you get not quite 40 gig operations peak, and we said maybe $112. The numbers coming out of that clock and power is our best engineering estimate based on SIM. The price is a completely wild guess. Now a caution. That's 33 total operations peak. They're independent MIMD operations. They can be any mix. Well, not any mix. It's not, as so often happens, counting each SIMD as a separate operation. So a vector operation in this count is one operation, not 16 or however many. If you count individual vector elements, we're looking at maybe 500 operations per cycle, but we're only talking 33 as MIMD. Furthermore, the ops in the instruction must match the functional unit population in the hardware. You cannot do more multiplies than you've got multipliers. So that's 33 total ops distributed across what the architecture can do. It's not 33 adds. In fact, on Gold, you've got 8 ALUs, so you can do 8 adds, but you can't do 33 adds. Well, if you're doing 33 operations per cycle peak, why? And the answer to that is 80% of code is in loops. Pipeline loops have unbounded ILP. You can fill up all the functional units you've got, unrolling the loop if necessary. But if you can do a pipeline, you can fill it. And this is what things like stream processors do, because a stream is just a software pipeline that's being driven by a device at one end, and they can be as wide as they can handle the data. And make use of those operations. So DSP loops are typically software pipeline, and you can do the same if you can software pipeline. The catch, of course, is that you frequently, in general purpose code, and the mill is a general purpose architecture, it is not a DSP. General purpose loops frequently cannot be pipelined, or more correctly, most architectures cannot pipeline many general purpose loops. The solution, which we've adopted. First, we alter the architecture so we can pipeline almost every loop. And we throw function hardware at the pipeline. The actual adders and multipliers are a tiny portion of the power and area budget of a chip, typically well under 10%. Nearly all of a chip like a Haswell or something like that, the power and area is spent figuring out what you're going to do next, buffering data, organizing it, getting stuff from one place to another place, and finally you do an add. The add is a tiny portion. You could triple the number of functional units in there, and you would not even see the difference in the power and area budgets. The reason why they can't is because they can't feed triple as many. We can. The result, after all these steps, is that loops have dropped from 80 to less than 15% of cycles. Now, of course, 33 operations per cycle peak. The question becomes, how do you do that? It turns out the biggest single problem is decode. If you use fixed length instructions, it is easy to decode. You just have 33 decoders and drop 33 32-bit instructions into 33 decoders, and Bob's your uncle. You're there. It's easy to parse, but if you have 33 of those and they're 4 bytes apiece, you're looking at a single instruction being as much as 132 bytes. And if you're trying to get 132 bytes per cycle out of your instruction memory hierarchy, well, good luck. That's a truly horrendous quantity of byte streams to get in. Ouch. Furthermore, for practical reasons having to do with latency, you're probably restricted to an top-level instruction cache of 32K, maybe 64K, but 32K. And if each instruction is 132 bytes, you're only putting 250 instructions in that thing. And as a rule of thumb, you need at least 1,000 instructions in your top-level iCache, or you'll spend all of your time thrashing your instruction stream out of the second-level cache of memory. So you need to get more in there. Well, an alternative is to use variable length instructions. The x86 is sort of the gold standard for instruction density. It does use variable length instructions. The recent additions to the instruction set have made it slightly more spendthrift in bits, but it's still a whole lot better than most. The problem is that it's very hard to parse. The x86 does absolute heroics, essentially starting a decoder at every possible byte boundary. At least some of them used to do that. They don't do that anymore. They're more pessimistic and buffer the instructions instead. But they are able to parse, even the most recent x86 are able to parse only 4 operations per cycle. That's not 33. Our invariable length, we are variable length. The mill is a family, and the actual instruction density varies across the family, but 17 bits per instruction or per operation is a reasonable average. So 17 bits times 33 ops, we're only looking at 70 bytes. That's much better, much more tractable, but it's still painful. Your instruction cache pressure, well, you've doing better here, but you still only got 500, which is quite a ways from having 1,000 in the top-level instruction cache. Well, what are we really trying to do here? We're parsing a stream of instructions. The logical model is that there's a program counter, and which points into memory or into the address space at a stream of instructions, and those are fed into decode, and the decode instructions are fed into execute. But what really happens is that you're grabbing a whole bunch of instructions, feeding them into multiple decoders, and trying to do that every cycle. If they're fixed length instructions, it's easy, but they're big. If they are variable length instructions, well, it's easy to know where the first one starts, but where does the second one start? Well, it starts after the end of the first one, but you don't know how big the first one was until you've already parsed it. This is a linear parse, and it gets very large. It's a very large polynomial function. It gets real bad real fast with increasing numbers. You can do that if n is 3, but not if n is 30. However, because it's polynomial, 2 bundles of instructions of length n are a whole lot easier to parse than 1 bundle of length 2n. So what you can do is split each bundle in half and have two streams of half bundles. A bundle is the collection of operations within one instruction. So you wind up with two streams of half bundles with two program counters. One program counter looking at one stream of half, which with its own decoder. The other looking at the other stream of halves with its decoder, and the two decoders are feeding the common execution unit. You have two physical streams, but there's only one logical stream. It works just as if we were working off a single stream, except that we physically split them in memory. The problem is, how do you branch one of these? We have two program counters. So if we take a jump, we need two program addresses. On the middle, we organize our code into extended basic blocks, also called super blocks. These are sequences of instructions with a single entry point, possibly reached from a number of other EBBs, and potentially multiple exits. A basic block is single entry, single exit. This is single entry, potentially multiple exits. So everybody will enter at the top, but the EBB will exit out one of those branches. Well, if we're organizing our code as EBBs and we have two streams of halves, what we actually wind up as having two streams of half EBBs, which are connected to each other via branch operations as per a perfectly ordinary code organization. But because there's only a single entry point, all of the half EBBs are entered at their top. They may exit from the middle, but they'll only be entered at the top. It is not possible to jump into the middle of an EBB. So take two half EBBs. The colors here match. The two dark blues are the two halves of one instruction. The two browns are the two halves of the second instruction, and so forth. These are laid out somewhere in memory. Remember, they're two physical halves, but there's only one logical set of instructions here. There's only 4 instructions of this, although there's 8 bundles. Now we reverse one of these in memory. The two halves are each the same color, so when we reverse it, that's what happens. We now can organize it by butting the two halves to each other end to end. Like so. We now have got a single entry point, which is in fact the entry point for both program counters. And once we've jumped in there, one program counter will move toward higher addresses, and one program counter will move to lower addresses. So if we do a loop, we compute the effective address. That effective address goes to the middle of the two halves and sets both program counters to that address. Now we still have 2 decode engines and 1 execute engine. So the first thing that will happen is we'll peel off the 2 half instructions, drop them into decode, and the result will go in execute. And we will then advance the program counter to the next. That in turn means grab the next pair of half instructions, decode them, execute them, and advance yet again. And so on. The physical layout of doing this, on a conventional machine, you've got the I cache sitting on one side, and in between the I cache and the execution unit is the decode unit. There is a critical distance as you're organizing this thing and laying it out physically on a chip. That critical distance is the distance from the far side of the top level instruction cache to the decoder, because that wire length is going to determine the latency of fetch. And many, many things depend on the latency of fetch. It determines your pipeline length, what your mispredict penalty will be, and so forth. And you need to keep it short. As a consequence, the top-level instruction cache has to be small, which is why typically 32K is a typical number. Because if you make it any bigger, what happens is that your critical distance increases and you're paying for it in latency. The mill, however, doesn't have to do it that way. Because we have two decoders, we can also have two instruction caches, one feeding each decoder. Note that those decoders are the same size as the conventional, but the total amount of instruction cache is the same as the bigger. So we have the latency of a small cache and the capacity of a large cache. The critical distance is the same as the small cache. Now, splitting 33 ops in half means we're down now to 17 ops. And parsing 17 ops is more than most variable length systems can do, more than any variable length system before can do. And unfortunately, this is a highlights talk. There's just simply not room in time to go into the depth which is present on the videos which are on our website, and I encourage you to see for yourself how it is that we can parse 17 ops per cycle, more correctly, 17 ops in 2 cycles in the pipeline. We do. And how we do it is on those videos, but I have to skip over it now or we'll never get out of here. So much for encoding. Besides the decode, the other problem is data. How do you feed 30 ops worth of data into an execution engine? The wire complexity is, if it were being done in a conventional out-of-order superscalar, it would be simply impossible. They're already saturating it with eight execution units. So how do you feed them? Every cycle. This is peak, but it's a sustainable peak, and our power budget is low enough that we're not facing the dark silicon problem where the marketing departments of all major chip vendors these days lie. They tell you you will get so many operations, but if you actually try and do get so many operations, you'll discover that the power throttle has cut your clock down to somewhat less. The basic problem is that there's lots of data sources. This is a typical set of numbers that, in fact, the numbers from Haswell. My compliments to Intel. I use Haswell as an example because Intel is more than usually forthcoming about architectures compared to other vendors. So it's not that Intel does it any worse than anybody else. In fact, they tend not to do. They do a very good job. But they also make their numbers available so I can cite them. So that's nearly 500 sources. There's a lot of consumers, nearly 100 sinks. The cost, well, any one of those sources can get to any one of those sinks. So the number of levels in the distribution hierarchy to get from all the sources to all the sinks is log the number of sources. And roughly, the power is roughly proportional to the product of the number of sources and number of sinks. That's 9 levels, which adds at least 3 more pipe stages, depending on what your clock is. And that data distribution consumes a very large amount of your power budget. This is your ceiling in a conventional out-of-order superscalar. So why have so many sources? There's really only 32 registers. Why are there 300 plus rename registers? Why do rename? Well, if that's your source code, and you will be naturally converting it into that kind of an operation where you're making use of a temporary for the intermediate result. If you wind up using the same register, RT, for the two intermediate results, you'll discover that you are not able to execute these in parallel. You do one of them, and then there's a cycle boundary, and you do the other one, but you need to split them because they're actually independent, and you don't want to be forced to sequentialize them because they're sharing a register. The hardware does a hardware rename. Compilers can also do rename, but for out of order, the hardware does it. So instead of RT, we have RT1 and RT2, and the hardware turns the code into something like that and exits. This does, in fact, speed things up, no argument. The problem is it's the cost. Why does the compiler reuse those temporaries, forcing hardware rename? Well, sometimes because it runs out of registers. It just has so many things it needs to manage. Or not, the Itanium has got just a slew of real registers. There's no easy way to mark the last use. There's been various instruction set considerations of how to do that, but nothing has quite worked well. So there's no way for the compiler to tell the hardware, oh, you can reuse this register. And there's also problems passing arguments to calls because you don't know whether the called function is going to use the register or not. What are those temps used for? Of all program-created values, roughly 80% are referenced exactly once. That is, the register is not a data storage device. It is a naming device in order to pass data flow from one operation to another operation. It is purely a connector. It is not a data store. 14% are referenced 2 or more times. Here, we are going to use something several times. We put it in a register, and it hopes it stays there because it will be faster when we need to get access to it later rather than going to memory. The registers are a fast source of memory. 6% are never referenced. This is coming from a study by Sang and Pat. Yale Pat has a tendency with his crowd of students to produce interesting papers. I found these numbers very interesting. So split the uses. Why have the same mechanism for all of them? You need one mechanism for local memory and one for data flow. You can ignore having a use for the things that are never going to be used. Are there any machines that do not use registers for data flow? You bet. An accumulator machine. Result and one source are implicitly addressed, not passed through a named register. It's in the accumulator. Stack machines, both sources and the result are implicitly addressed. The problem is that both of these have no parallelism. A stack machine, the way it works is you take the two values off the top of the stack, feed them through a functional unit while it does its thing, and push the result back up on the stack. But because there's only one top of stack, you can only do one of these at a time. Where did all your parallelism go? Stack machines are wonderful. The very first compiler I ever wrote was for a large-scale stack machine, the Brosby 6500, and it's a marvelous target for compilers, but you can only do one operation at a time. So what you really want is several stacks, like so, except that you want to be able to have them interleaved because you want people to be able to pick values out of each of them, so that any unit can reference any value. We pick a couple of values off of the stack, run it through the adder, and the result winds up back on top of the stack. Now, with this kind of a structure, I could have multiple adders, and they're all running in parallel. We call this mechanism the belt. It works like a conveyor belt. It is a fixed length FIFO. Whenever we want values to feed into a functional unit, say an adder, we can pull values out of anywhere in the belt and drop them into the adder. The new results coming out of the adder go to the front of the belt, and because it's a fixed length FIFO, new things being pushed on the front always push values off the back. You can do multiple reads in parallel. And all the results that retire in the same cycle all drop together. Note that 3 dropping on the front means 3 get pushed off the back. When you're addressing the belt, belt operands are addressed by relative position. There's no R4 because there's no registers. The mill has special registers like the real-time counter and things like that, but there's no general registers as we know them in most machines. So belt operands are addressed by relative position. So an add operation will say add the 3rd position of the belt to the 5th position of the belt. Note, you don't have to specify a destination address. That was always going to the front of the address. Remember I said that mill operations were an average of 17 bits? Well, one of the reasons why it's 17 bits as opposed to 32 bits is they don't have to encode a destination register. Have to encode your sources, but do not have to encode your destination. So if that's the belt, B3 is that red job, and B5 is the purple one. So the belt index is from 0, so B3 is the 4th most recent value to have been pushed onto the belt. B5 is the 6th most recent. This is called temporal addressing. You're addressing the stream of results in time order rather than in location position. A consequence of temporal addressing is that the address of a datum changes as more values get pushed. That red job, which is B3 now, when new values get pushed on, that red is now B6. Same value, new name. It's up to you to keep track of this, or more correctly, the compiler's code generator. I will say that keeping track of this by hand is not an exercise you want to try. The mill is not intended to be a good assembly language target. It's intended to be a compiler target and has been designed. Now things get dropped off the back, so it's a matter of use it or lose it. The compiler schedules producers near to consumers. You want the best code as if the value hits the belt immediately before when the consumer wants the value. So as a result, most things which are being passed through data flow style go on the belt, get picked up by the consumer, and the fact that they've fallen off the end is irrelevant. Nearly all single-use values are consumed while they're still on the belt. Different members of the family have got different length belts. We set the belt length so that the typical lifetime before a produced value is going to be consumed, it will still be on the belt. And what that lifetime is depends on how many producers. A tin at the low end can be dropping perhaps a maximum of 4 results onto the belt in any one cycle. And typically will only be dropping 1 or 2. So a belt length of 8 is enough for it. On the other hand, a gold or something like that at the higher end with potentially dropping 20 or 30 results at a time needs a much longer belt in order to have them have a reasonable lifetime. So one of the configuration factors in defining a family member is how long to make the belt. The belt is single assignment. You cannot change a value in the belt. Once a value is dropped, that's all it's ever going to be. As a result, there are no hazards. There's no read after write, no write after read, or any of the other hazards that if any of you have ever worked in the back end of a compiler, you know what a pain figuring out what collisions and hazards are and arranging to avoid them. And that simply doesn't exist on a mill. There's no need for rename registers. There's no collisions, so you don't have to rename. Instead, you have 8, 16, maybe 32 different belt positions, not 300. In terms of sources, remember we were back talking about power and how to do this? Instead of having 500 sources, well, guess what? We wind up having 40 or 50 sources. This rather sharply reduces the number of stages required in the pipeline and the amount of power consumed. However, long live values will not stay on the belt. They'll fall off the end. So they have to be saved. Where they get saved to is a hardware device in the core. This is not memory. This is in the core, called the scratch pad. There's a spill operation that will copy a value from the belt onto the scratch pad. The scratch pad is byte addressable statically. It is a place for holding values. It's not an array. You can't index into it. It has no memory address. It's a place for saving things. And there's a fill operation that will load the thing back up again. The scratch pad is framed local. The program illusion which we provide just is that each new function call gets its own scratch pad. In fact, what happens behind your back is different. You program as if this were true, and the hardware conspires to make it so that your program will still work. CPUs actually very rarely do what the program model says they're going to do. Thus, for example, the program model on all your laptops here says that they'll execute operations one at a time in sequential order. Well, that's the program model. Well, let me tell you, the hardware is not doing that. And similarly, with the scratch pad, you don't actually have one for each frame, but we can provide you the illusion that there is one. It is fixed size, and you have to explicitly allocate it on a per function basis, saying how much scratch pad you're going to use. The compiler keeps track of all of that. It's static byte addressing. Everything has to be aligned, no indexing, nothing like that. And there's a 3-cycle spill to fill latency. This means if you need to save a value and then get back again, it's going to take you 3 cycles to do that. This feeds back into the length of the belt. You want to set the belt length so that the average data value will stay at least for 3 cycles on the belt, so that if you need to run it out to scratch pad and back, you can. It's part of the configuration process to balance these numbers. The belt handles multiple results just fine. Take a divide operation, which is a pain in every instruction set architecture. They're all special purpose kludges. You may have a dedicated registers, you may do register pairs. There's this solution, that solution, and none of them are anything but ugly. Why? Because divide produces 2 results, quotient and remainder. And all the architectures, all the instruction set architectures are all designed to support 2 in, 1 out. Now we have 2 in, 2 out. It doesn't work right. Well, the 2 in is no problem on a belt. You feed the 2 in into a divide function, just like you do feed it into the adder. However, divide takes a while, so there's a clock boundary. And after some number of clock boundaries, the divide functional unit is ready to produce its results. And there's the final cycle boundary, and it can simply drop 2 results onto the front of the belt. Works just fine. Function calls. Let's assume that this is the caller's belt. We're at the start of everything. And we do a call. Semantics of a call is that you get an argument list of belt positions. So this function has got 4 arguments, and they are respectively B1, B5, and 2 copies of B3. Cycle boundary, we're now into the callee. The callee starts out with an empty belt. He's got nothing in it. This is not like registers where you can browse in your caller's stuff. That's a security hole. We don't do those kinds of things. So the callee winds up having an empty belt, which is populated with the actual arguments. Double pink line means some number of cycles the callee executes. And let's assume at the end of that execution, that's what we have for the callee's belt, and he's prepared to do a return operation, returning the V4. Well, the return operation also restores the caller's belt. There it is, just as it was before the call. And what the return operation does is simply push the return value onto the front of the caller's belt. That is, call works just like add. You give it some arguments, it has some results, the results gets pushed on, but everything else remains unchanged.
What if you have more arguments than
They have to be passed in memory, just like if you run out of registers, and using much the same mechanism. Ditto var args and other things which would be a nuisance in registers. They're also a nuisance on the belt.
So when you say memory, is that scratchpad?
Again?
When you say memory, is it scratchpad or is there?
Scratchpad is not memory. You cannot pass in the scratchpad. That is exclusively local to each frame. So a call has belt effects, just like an add. And it works just like divide. You can have a call which produces multiple results. That save and restore mechanism is handled by the spiller. This is a hardware state-saving mechanism. Various machines have had hardware state-saving mechanisms, the Spark, the Itanium. It's not at all uncommon. We take it perhaps further than most do. These talks do not cover the spiller. There's an upcoming talk that will be covering the spiller. But if you're interested, you can ask questions and I'll answer what I can. The way it works is that values on the belt are actually kept in output registers and buffer registers and are marked with the owning frame. Each new frame gets your frame ID. The belt accesses only to the values which belong to the current frame. So consequently, if you change the frame ID, your belt is now empty, because all of the values that had the former frame ID are not your frame ID and you no longer can reference them. However, they're still there and can be spilled in background at your leisure. Arguments are passed by copy. The copy gets a new frame ID. This is how arguments are passed. It's perfectly possible to have a value. Remember, things have got an explicitly exposed latency. It's perfectly possible to have a value which is in flight over a call. Say we've got a multiply. Multiply being taking some number of cycles. And after the first cycle, we now do a call. Well, assume that nothing retired in that cycle, so we've got the same belt. We now do a call. Cycle later, we're now in the callee. And the multiply now has a result. We're still in the callee. Do we want to drop the multiply result into the middle of the callee when the multiply was started in the caller? No. So let's rewind this a little bit. We're still in the callee for some number of cycles. We're now returned with the result. We're now back in the caller. Notice that the belts are now the caller's belt plus the call's result. And now the multiply retires. That is, from the viewpoint of the belt and all in-flight operations, a call is an atomic operation the same way an add is. Calls are atomic. In-flights retire after the call returns.
Where do they wait?
In the spiller.
There's another stack that has intermediate results. You have many intermediate results, right?
Let me defer that until later. I'll answer as best as I can, but it would take us too far afield.
Okay.
It's good that calls are atomic because interrupts and traps are just calls. They're involuntary calls that the hardware called for you, but they're just calls. And consequently, when you return from your call, things like your belt, your scratch pad, and other machine state, it's as if the interrupt never happened. But the mechanism is identical to a function call. And as a result, we don't have to have all of the funny things of a duplicate set of trap registers or supervisor mode that you enter. It is identical to a function call. They're just involuntary calls. The hardware does the normal vector and lookup. Hardware supplies the arguments. There is no doubled state. There's no task switch. There is no pipeline flush, no more than there is for a regular call. There is no restart penalty after the return, no more than there is for a regular call. And your only penalty is because you did not anticipate you were going to get interrupted is a mispredict penalty. And the mill has an extremely short pipeline, and the mill's mispredict penalty is 4 cycles plus the cycle time of the top level cache, or if you had to go get the code from memory, a memory load, or whatever it is. But 4 cycles plus the memory access. Brief interrupt. Dave, if you need a parking certification, you need to get it from Roxana because they will boot your car if otherwise. Art doesn't have this problem. He came on a motorcycle. There's, of course, a catch. There's always a catch. The catch is the same catch that every wide, statically scheduled, exposed pipeline machine has. And that is that they only work if you can know exactly what the latency of the operations are going to be. Because if you don't know what the latency is and it turns out that you have scheduled it wrong, you're going to stall issue until you've caught up with yourself. So it requires a compiler known latency. If the latencies can vary, the compiler has to assume the common case, and if it's wrong, then everything stalls. Well, not everything. You've got a lot of background processes. The spiller and so forth keep running happily. This is the bane of VLIWs and other such statically scheduled machines, and why they are restricted to the dark nether corners of the DSP world, because the DSP world can arrange itself so that they don't ever miss latency, and you can't do that in a general purpose code base. The mill is a general purpose architecture. It is designed to take code straight off the internet, the same stuff that runs on your laptops, and run it just fine, thank you. It is not restricted to DSP-like loads. It's a general purpose load. Consequently, we cannot tolerate these stalls. This, of course, is the standard problem with VLIWs. The mill is not really a VLIW, but in many ways it's like a VLIW in terms of its encoding. In practice, while there's early out ops and so forth, the only varying latency op that really matters is load. The memory hierarchy, well, if you find something, and this is what the compiler has to assume you're going to, you find something in the top level cache, 3 cycles, Bob's your uncle. No worse than a multiply. Got to go down a level, 10 cycles in modern chips. Got to go to DRAM. See you next year. This is the load problem. This problem is not unique to VLIWs. Every machine has this problem. You write add, load, shift, store, and execute that, what you're going to get is add, load, stall, 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 stall. For a change, maybe we'll stall. So no, the result's back. We now do a shift. Store. This is the reality for every machine. They all have to deal with this. So the goal is to hide memory latency. There's a general strategy. The general strategy is you ignore what the program said in terms of program order. You issue operations as soon as their data is available. You issue loads as early as possible, as soon as the address is known, sometimes even before that. That's called prefetch. And you find something else to do while you're waiting, because you are going to wait. There's two basic strategies of finding something else how to do. One is the hardware approach. It's called dynamic scheduling. You organize things so that you buffer all the operations that haven't been issued, whose data isn't available yet, and then you keep track of which ones are available. This comes from the Tomasulo algorithm, from the 360, and Mr. Tomasulo were to see a Haswell, there'd be a number of things which would greatly surprise him, branch prediction being one of them. But the way out of order works would not surprise him in the slightest. There's been no real fundamental improvement. The software approach, static scheduling. You use an exposed pipeline, and you simply expect that the value is going to show up from the top level cache, and while you're waiting for it, you put up other operations which are independent in the delay slots. Dynamic scheduling of hardware, you have to decode ahead because you're going to need to buffer a lot of instructions. Track operations whose values are not yet available. Issue ready operations. And as they retire, update everybody who was waiting for that result so you can find them again. This is an immense amount of very power-hungry hardware. This is why your laptops get hot. The good side of that is it does hide cache latency and misses, so long as there's anything else to do anyway. Obviously, if there's nothing else to do, you may have got nothing to do but wait. However, there's drawbacks. It is window limited. You're only able to schedule operations which have already been decoded, and the amount of space you got for buffering instructions is fixed and relatively small. Consequently, while there may be other operations you could have done, if they're not in your instruction window, you can't do them. But what's truly ugly about it is it's incredibly expensive in area and power. The software approach. Well, the compiler does the work. It determines dependencies amongst operations, schedules producers to retire just before the consumer, schedules independent operations to issue together and in parallel with things like executing loads, schedules loads as if they will always hit in the top level cache. The good, cheap, low power. These days, easy compiler, because compilers do this, have for a long time, fast. Don't have no window limit. The compiler can look over your whole program. The bad? Well, there's some limited latency, which limited low concurrency, which is probably a tighter constraint than what the hardware equivalent has, but this is not really a big factor. What's truly ugly about it, if you do a miss, you're in trouble. Well, we too had to address the load problem. And what we did is we factored the problem to recognize there isn't one load problem. There are a bunch of load problems. Some loads will always miss to DRAM on every machine. If you're doing random access, truly random, to a hash table that's bigger than your cache, you are going to be running at DRAM speed, no matter what chip and what architecture you use. There's no alternative. Some loads also have to wait for data-dependent things, data-dependent addressing. If I'm, for example, if I'm chaining down a linked list where if I have to load the address to the next one and then load the address to the next one, then load the address to the next one, these fundamentally are serial. You cannot do them in parallel no matter what, and no machine can. You may be able to do speculative prefetching, but that's a different problem. We're talking about loads here. No CPU has a solution to this. Not the mill either. Some loads depend on control flow. Woo. Why am I being madly running ahead here? Excuse me? There we go. Here we have a situation where we can't do the second load until we determine that the first load did not trap. That's to provide correct program semantics. Many hardware, beginning especially with the AFOs, notorious for this, essentially ignored this issue, and proper sequential execution was deemed to be unimportant. But what you actually have here, this isn't a load problem, this is a speculation problem. You want to be able to issue the second load speculatively and not have something go wrong if, in fact, the first load answered your question. This is a speculation problem. If you can solve the speculation problem, this turns into one of the other cases. Mill speculation is a subject to a future talk. If you go to our website and sign up on the mailing list, that will be announcements for these talks. I showed you that we're giving highlights of the first 3 talks, but there's at least a dozen talks in this series. The mill has gotten a whole lot of novel stuff in it, and it's not a one-trick pony, and it's not a one-talk architecture. So sign up, and you will find out all the rest of the stuff that I'm not talking about today. Then, some loads come in groups with a regular addressing structure. An example is iterating over the elements of an array. You can, in principle, fetch every element of the array, all in parallel. And in fact, this is one of the things that the out-of-order architectures do pretty well, despite the power costs. However, this too isn't a load problem. This is a prefetch problem. So long as you have all of those values coming in at the time when you need it, you can treat yourself like a DSP, which does exactly the same problem. They will iterate over an array and arrange for it that values are prefetched in at the right time. Guess what? Prefetching is the subject of a future talk, and you can sign up for it at our mailing list. So what's left after defining certain things as being non-problems, or at least future problems? Some loads come in independent bunches. A plus B plus C, load A, load B, load C. Have all the loads run in parallel. Some loads miss. You need a way to hide the unexpected additional latency. Out-of-order hardware handles these cases. It does a very good job of handling these cases, assuming that there's something else that it can find to do. And if it can't, then you can't do anything anyway. Out-of-order really only handles these cases. The mill is a competitive processor, and consequently, so long as we do at least as well as out of order in terms of performance, we're happy because we have vastly less power consumed for the process. Here's a quote I love. The dirty little secret of out of order is how little out of order there really is. That quote is from Andy Glue, who did a number of Intel's and AMD's x86 chips and is well known amongst the cognoscenti. The mill mechanism is called a deferred load. Here's a generic mill load operation. You say load, opcode. Then there's an address. There's a bunch of address modes. It may contain a 64-bit base, a up to 32-bit offset, and optionally a scaled index. So far, so conventional. Then you have to say the width, or how big a thing are you loading? Mill defines support for 1, 2, 4, 8, and 16-byte operands and vectors of each of those. The vector size is defined on a per member basis. Tin, for example, has a vector size of 8 bytes. You can do 8-byte vector, 8 1-byte vector operations, but if you're doing a double precision, your vector is a length of 1. Tin is our extreme low end. However, there's another argument there, the delay. This one you've not seen before. The delay specifies the number of issue cycles before the load shall retire. This is explicit. It's not an implicit 3 cycles because that's what L1. The load says when you want the result. Thank you. So a load would look like that. Some address, some width, and the value 4 for the delay. The load issue is there. Cycle boundary, instruction. Cycle boundary, instruction. Cycle boundary, instruction, and one more with feeling from the top. And at that point, the load is going to retire, which of course is where we're going to put the consumer. How do we know it's going to retire there? How do we know the data is going to be available there? Because we said so. That 4 means that the retire is deferred for 4 instructions. Why did the compiler say 4? Because he had 4 instructions he could do. That simple. If he didn't have 4, if he had 7, he'd put 7 there. If he had 2, he'd put 2 there, or whatever.
So this is like per instruction instead of the CIDR 5's MLR.
Again?
So this is per instruction?
No, this is per op. Each load op has its own latency.
Like a CIDR 5, but the same thing, but a global MLR, right?
Each one has its own. Even if there's multiple loads in the same instruction. So let's compare how this works to the hardware dynamic and the compiler-based static of the LIW. Assume for the moment first that there is nothing to do but wait. That nobody, neither the hardware nor the software, are able to find any independent operations that can be done in parallel. We're going to do the load and we're going to wait for the value to come back. That's that random access problem. Static, well, because the static is going to assume 3 cycles, it's going to have to insert a couple of no-ops to fill the extra cycles. The dynamic hardware doesn't put in any no-ops, but it's going to take 2 cycles worth of stall before the result came back. The deferred is going to look very much like the static. We know that it can't come back any sooner than the 3-cycle latency of the L1, so we require a minimum of 3 cycles in there. So we too encode 2 no-ops.
Does your instruction encoding not allow you to say 0 there instead of 2?
We actually, you say 2, and it encodes a 0.
So then values of 0 and 1 are not available to you?
No, you can write 0. Excuse me, if you write 0, they'll complain. The assembler will complain. For user interface simplicity, the number there is the number of intervening operations.
Yeah, no, I understand. I was just wondering about compressing out the no-ops.
Patience. All three of these have the same performance. They take 3 cycles. As described in the first full talk, remember this is only a highlights talk and I can't cover everything, but as described in the first talk, no-ops occupy no space in the code nearly always. A no-op encodes as 0 bits. And how that works, well, go see the talk and on the website. Yes?
You're on slide 67 and we stopped in 8 minutes. Are you going to have some comparative performance between mill and other computers?
No. This is a description of how it works, and I am not going to attempt to do benchmarks. We're nowhere near being able to do major benchmarks anyway.
So does the efficiency of these ideas matter? I mean, these are interesting ideas, but in computer architecture, like you said, you grade comparative.
What I'm describing is the interesting ideas. That's what these talks are. They're describing the mechanism. We're not attempting to sell you a chip with benchmarks because we don't have a chip to sell.
Let's talk about loads. You have a lot of ideas. It's easy to come up with a lot of ideas. We'd like to know how well these ideas work. Do you have an evaluation how well the loads work for real programs?
As I said, no, the talk is not going to talk benchmarks.
If I went to all 12 of your talks with one of the talks?
In general, we're not talking benchmarks. These talks are describing the architecture.
I think the worry is, well, it's an obvious worry, but what I'll just point out is, the Itanium was sold to people on the basis of a few hand-assembled loops, apparently.
A lot of interesting ideas.
Okay.
And that was $1 billion plus.
Gentlemen, it would be easy to say, gee, I don't think it's going to work, and feel free to do so.
It's easy
But,
to have ideas if you don't evaluate them.
So I guess one concrete thing is, so you must have a compiler, I assume, as a compiler person.
Well, maybe we should
Can this be deferred until the end?
do you have
I can see that this is going to lead into an extensive discussion, and I'm never going to finish.
you only have 5 minutes and you're leaving. Do you have a compiler?
We are not in a position to be compiling serious benchmarks today. If you can look at the architecture, for example, the business about running the code end-to-end so we can have double the size of the cache. How much of an advantage that is not clear and won't be clear without the kind of benchmarks that you'd like to see. But I think you can see that inherently it must be an advantage of some scale.
No, absolutely. There's no ideas that are not, new ideas are not always good.
So the worry we have, the worry here is you're building a statically scheduled machine without a compiler that can run serious benchmarks. That seems like an anti-pattern. That's how do you build a statically scheduled architecture without a compiler that can look at lots of code?
If you would like me to wait and describe these things in 2 years, when we have a ported operating system, an LLVM-based compiler, we're in the course of converting to the LLVM, and a running chip with pins on the bottom in order to produce all of that, by all means, do not come and see any of our talks. But I feel that it is important for us to give back to the community and expose people who are interested in architecture as raw architecture to say, hey, here's an idea. And that's what the talk is.
Yeah, we appreciate the ideas. It's just a little difficult to again, the ideas look interesting, and that's why.
He's asking us to...
Then permit me to finish, because there's more interesting ideas. That is all I'm here to show you, is interesting ideas. Okay? To return. Let's take another case. Let's assume that there are operations which can hide at least the $1 latency, and we do hit in the top level cache. In the static case, it will assume that it did. It will schedule 2 ops. The retire will occur there, and then it will be able to schedule more operations. The dynamic case will find those same operations, retire at the same point, and the behavior will be identical. It will find the same operations or equivalent operations to what the compiler found. On the deferred case, we will have scheduled it as a load with 5, because we've got 5 operations to do that with. It won't retire until 5, but it doesn't matter because we're not using any of those. These are 5 independent operations, so the fact that we had to sit on the value for a couple of cycles doesn't matter. All 3 are the same performance. Here's where we have a difference. Assume that we had 5 cycles, but we missed. The static case is going to turn into something like that. It will have scheduled 2 ops. It missed, so we'll have a set of stalls, maybe many cycles of stalls if it actually wound up going to memory. And only when it retired is it able to execute the next operation. Dynamic does much better. It will find all 5 operations, do them, and then if we had to go to memory, then it will stall, but it will have found all 5. The deferred case will have scheduled all 5, uses them, even though there was a miss, and if we had to go to memory, we'll take the same delay that everybody else. So in that case, the deferred winds up being the same as the dynamic case, but beats the static case. Yes?
Okay, when you've got an add unit, you can schedule and retire every cycle. If you've got a load unit and you're saying wait 5 cycles, doesn't that mean that unit's not available for another load?
No, each load unit can issue every cycle.
Fully pipelines, as many cycles?
You need to look at the third talk for the machinery of how that works, but essentially the load unit, all it does is fills the memory pipeline with a stream of requests and allocates a retire station buffer which accumulates the values coming back from the memory hierarchy, and that buffer knows when it's supposed to retire, and it retires. So if you've got 2 load units, you can be issuing 2 loads per cycle forever.
We have like sort of a minute to wrap up. So we have to leave it.
Well, we'll run off the end without any problem. Let's leave that. There's no point in beginning something which takes longer than a minute. There's a whole lot more about the memory stuff, and that's in the third talk. I'll skip forward to.
I was waiting for this to show up, but since we're out of time, I'm going to ask you a question. What if, like, the compiler said comma 5 and the data can't come back in 5 cycles? Do you install the machine?
Again, please?
What if the compiler said comma 5 and it scheduled 5 ops in between, but the cache, the miss was actually all the way to DRAM, and the machine cannot give the data back in 5 cycles?
Then we will stall. But every machine will stall because you only had 5 things to run in parallel.
Sure.
Out of order stalls all the time if it can't find anything else to do.
Sure.
And the bottom line on this, there's actually a few very special corner cases in which an out of order can do better than the mill, and a few in which the mill can do better than the out of order. But these are roughly offsetting, and in just over or the average over code, we wind up having the performance of out of order, but the power usage of static.
Okay. Thank you, dear. Let me round this out.